working on polar form of complex number. In this tutorial, we'll work on proving algebraically the product of two complex number and the quotient of two complex number, and then we will interpret geometrically, which involve enlargements followed by rotations. Okay, let's move on. I encourage you to pause the video and try first. So the polar form quickly leads to an elegant geometrical interpretation of the multiplication of complex number and quotient of complex number. Okay, let's start with multiplication of two complex number. Let it be z1. z1 is equals to r1 into cos of theta 1 plus sine theta 2 theta 1. So z2 will be r2 cosine of theta 2 plus I sine theta 2. Okay, let's find the product. z1 times z2. In this case, we are going to multiply this. So since r1 and r2 is the distance from the origin to that complex number, okay, so just directly multiply the magnitude or the modulus. So that leads to r1 times r2. Okay, now let's distribute here. Okay, cosine of theta 1 plus I sine theta 1 times cosine of theta 2 plus I sine theta 2. Okay, so let's just distribute cosine of theta 1 to cosine of theta 2 and cosine of sine of theta 2. That brings us cosine of theta 1 times cosine of theta 2, okay, plus cosine of theta 1 I times sine theta 2. We have I here. Okay, so now next let's distribute again sine I sine theta 1 to cosine of theta 2 and I sine theta 2. Let's bring it here. Let me write here. Okay, plus I sine theta 1 times cosine of theta 2 plus I squared, because I times I is I squared. So we have sine theta 1 times sine theta 2. Okay, we don't forget that we have r1 and r2 here, the product of the two, and actually we will write that at the end. Okay, so now let's combine. So we have here these two are similar because the square of I or I squared is the same as -1, so that changed this addition to subtraction. Okay, so this is the same as saying cosine of theta 1 cosine of theta 2 minus sine theta 1 and sine theta 2. So we're combining or collecting like terms. These are the same. We have again here the I part, which is I into, there you have cosine of theta 1 and sine theta 2 plus, there you have the yellow one, this one, sine theta 1 times cosine of theta 2. Okay, from your trig concept or trig knowledge, this is the same as the sum of the angles, which means cosine of theta 1 plus theta 2. Okay, plus I into, again this is the sum, okay, angle sum for two different angles. So this is the same as this is the same as the sum of the two angles in terms of sine of theta 1 plus theta 2. Okay, so finally we just come up with, still we never we just have this result, the product of the modulus. Okay, so this brings the product of the two complex number. Okay, now let's move on to geometrical interpretation. How are we going to interpret this in geometry? Product of two complex number. So let z1 let be z1 is here. Okay, let this is z1 and the argument is here. Okay, let's have another complex number, let it be z2 here. This is z2, so this is the argument for z2, and for z1 is this one. So the result of multiplying z1 and z2 here. Okay, so okay, let it be this is our complex number. Okay, this is z1. So in order to find the product of z1 and z2, you have to enlarge or multiply zy by scale factor of z2. Okay, so I'm gonna multiply this by z1. Okay, it goes this much, and then now we just first enlarge by z2, magnitude of z2. Now is rotation, so I have to rotate z1, okay, by the argument of z2. Let it be that is somewhere here, about the origin, anti-clockwise. Okay, about the origin, anti-clockwise. So this will be our result. Okay, finally this is just argument to z2, and then we still have this. All right, so when we combine, we have here at the end show. Let me use this one. Okay, let me use this one. This is it. Okay, this is it. This is argument of z1, okay, plus z2, okay, whose magnitude is r1 and r2. So the key here is when you multiply two complex number, z1 and z2, geometrically, in order to represent this, first you have to enlarge. Okay, you have to enlarge like z2 by scale factor of z1, okay, or z1 by scale factor of z2, followed by rotation. Okay, followed by rotation about the origin. Okay, about the origin O, and then anti-clockwise. But how much? Through, okay, through z2. Okay, this is how it works geometrically. So let's move on to the quotient. How are we going to represent this when we divide two complex numbers geometrically and algebraically? Let's prove first. Okay, let's prove. Let's find z1 over z2. Obviously, as you can see here, the modulus will be division. Okay, so that would be r1 over r2, and then we have cosine of theta 1 plus I sine theta 1 over cosine of theta 2 plus I sine theta 2. So this is the same as just if you remember rationalization, we're going to do the same concept here. So which means multiply both the numerator and the denominator by the opposite of the denominator, or cosine of theta 2 minus I sine theta 2 over, which means you have to multiply it by 1. Okay, nothing will be changed. Cosine of theta 2 minus I sine theta 2. Okay, this is it. Now just distribute. Let's distribute here. Okay, distribute cosine of theta 1 to cosine of theta 2 and I sine theta 2. Okay, let's do that one. That lists as cosine of theta 1 times cosine of theta 2 minus I into sine theta 2 cosine of theta 1. Okay, now let's distribute again I sine theta 1 for just the same thing here. Okay, let me use another color here. Okay, so that goes to I sine theta 1 cosine of theta 2, okay, plus, I mean minus here, minus, of course I times I is I squared, okay, sine theta 1, sine theta 1 times sine theta 2, sine theta 1 times sine theta 2, okay. So now let's combine. Of course we have here, since this is a kind of perfect expression from your real number, x plus y times x minus y is x squared plus y squared, but in this case, since it is a complex number, we have I squared times I squared, it becomes negative, so that leads to cosine of theta 2 squared plus sine theta to the whole squared. This is what we get when you multiply, when you distribute this and work with the other one, okay. The same is true here. So this is what we get. Now let's combine here, so this is going to be cosine of theta 1, cosine of theta 2, and bring this one here, because I square is the same as -1, so it makes this positive, so we have positive sine theta 1 times sine theta 2, okay. And now let's combine this two again, minus, you can have here, okay, let's take I squared in common, okay, or I in common, so you will have here sine theta 1 times cosine of theta 2. I just bring this one here, and then I am going to bring this one here, okay, minus sine theta 2 times cosine of, cosine of theta 1, okay. So over the result for cos squared theta plus sine squared, this is identity, so this is the same as 1, so over 1 I'm gonna leave it there, okay. So using cosine property of two angle sum, or difference of course in this case the angles, this is the same as cosine of theta 1 minus theta 2, okay, plus I, the same is true here, sine property of two difference of two angles, so this is sine theta 1 minus theta 2, okay. Finally this will be the result. Again, we have here of course r1 over r2, and we have here times finally r1 over r2. This is the same as z1 z2. So finally the quotient of two complex numbers is the same as the coefficient of their modulus of the two complex number times cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So we can come to generalize that when we divide two complex number, okay, just divide the modulus of the two complex number, that is 1, and then take the difference of the arguments of the two complex number to find the argument of z1 over z2 is the same as, we can say, argument of z1, okay, minus argument of z2. The same is true the modulus, just multiply, I mean divide the magnitude here. So how are we going to represent this geometrically? Okay, so let's have a coordinate here. Just pause the video and again try. Geometrically, let it be z1 and z2. Let's have, okay, this is z1, okay, with argument here, and then let's have here another complex number z2, Okay, Z2, let this one is Z1. So alright, so to find the quotient or the argument of Z1 over Z2, this is how we do. Okay, let it be the result will be this one. Okay, let's take one angle here. Okay, this is our Z1. So in order to find Z1 over Z2, we are going to enlarge, okay, Z1 by a scale factor of 1 over Z2. Means we are going to make it equivalent. We are going to divide. So as you can see here, it's just get it smaller. All right, because we're dividing. And then the next step is rotation. Rotate this through Z2, argument to Z2, okay, in clockwise directions. So let it be, this is Z2, okay. Now this is the angle for Z2, okay. Let it be this one, okay. So this is our final result. The final result is this one. This is our final result, which means, let me redraw here. That's all. So this is argument of Z1 minus Z2, and the magnitude is R1 over R2. All right, so in order to find Z1 over Z2, first, okay, this is the first thing, you have to enlarge, all right, enlarge Z1 by scale factor of 1 over Z2, okay. Obviously you're decreasing. And then the second is rotates, okay, followed by rotation through Z2, okay, through Z2, okay, clockwise directions. This is how it works, clockwise, about the origin. Geometrically, this is how you represent or region. Okay, this is how you represent geometrically the quotient of two complex number.